Hello everyone and welcome to our presentation. Today we are going to present our work on reverse engineering deep neural network architectures by exploiting application characteristics of just-in-time GEMM libraries. So let me start off by outlining today's presentation. First, we'll go through an overview to understand our work. Then we'll introduce some background and formally introduce the threat model. Next, we'll present our attack strategy along with the results, and finally, we will present our conclusions. So JAXED in one simple sentence is a deep neural network hyperparameter extraction attack. When we say hyperparameters, we usually refer to the number of layers, number of filters in a layer, kernel size, etc. And DNN operations are performed using highly optimized matrix multiplication libraries. And recently, we've seen a lot of research and development of just-in-time optimized GEMM libraries. DNNs actually have many applications. Example, increasing resolution of images from 720p to 4K. And companies do invest a significant amount of resources to identify best model parameters. And since it gives a competitive advantage over their rivals in the industry, companies increasingly treat these hyperparameters as intellectual property. DNNs actually consist of convolution layers and fully connected layers. Because convolutions consume a majority of the execution time, there has been a trend to optimize these operations using just-in-time GEMM libraries. So next we'll see how these just-in-time optimizations actually expose a side channel. In the first inference, the GEMM library generates a highly optimized instruction sequence, and in subsequent inferences, since we already have the instruction sequence in the code cache, it will only be retrieved. So this means that in the subsequent inferences, you can have fast execution. So next we'll see how this timing difference can be exploited by a potential adversary. For now, let's assume that the machine learning framework is shared. The victim first executes the model, so then this would check for the availability of the instruction sequence corresponding to matrix dimensions. In this case, M1, N1, and K1. So this is in standard GEMM notation. So since it's not available, it will be recorded as a code cache miss, and then it will trigger a just-in-time code compilation. And this would consume a certain amount of time. So this would be followed by the actual execution after the instruction generation. So afterwards, if an adversary uses the same parameters as the victim, so this means that the instruction sequence is already in the code cache. So this means that the code compilation is not triggered, and then it would result in an instantaneous execution. So next we will see how much of a timing difference we can observe using these two methods. So on the left hand side you can see libxsmm, which is a JIT optimized GEMM library, and on your right hand side you can see OpenBlast, which is a traditional GEMM library. So an isolated run in this case means that only the adversary is present in the compute environment. And a shared environment means that both the victim and the adversary are in the same compute environment, and also they're sharing the same parameters. So in the case of libxsmm, if the adversary is using the same matrix dimensions, they'll see a reduction in the execution time because the instruction sequence is already in the code cache. But with OpenBlast, we would not see a difference like that. So next I'll explain our attack scenario. There are actually two scenarios. One is where the attacker only has read access to a web API. And we will see that the attacker can gain an idea that there is a side channel vulnerability. But the second one is the most interesting one, where the adversary also has write access through a web API to their own model. So this means that the attacker can now perform an exploratory attack and then extract out model hyperparameters. So our first scenario would look something like this. A victim would send their model name, and then their data would be an image that they want to perform inference on. And then the adversary would do the same, where they build their own model and then perform inferences using their images. So in this case, if these two models share different operations, for example, convolution parameters, then the attacker would observe a reduction in execution time. So this would mean that there is a side channel vulnerability and the attacker has knowledge on that. But things get very interesting when you have write access as well. So in this case, adversary can modify their model in steps 1 and 3. So by changing the model parameters, the adversary times their own model execution time and then sees whether there's a decrease in the execution time. By analyzing these timing differences, the attacker can extract out model hyperparameters, as we'll see in the next sections. So this brings us to our formal attack model. So first we assume that we have black box access. So this means that the victim's DNN parameters are not visible to the adversary. The platform is shared. So ideally this means that machine learning framework and underlying libraries should be shared between the victim and the adversary. The last point is actually the most important one and the strength of our approach. So in our attack, the attacker doesn't need to have fine-grained timing details of the victim, and the attacker should only be able to time their own actions. So this means that the attacker can easily gain this timing information and then correlate those actions to figure out which parameters are being used by the victim. So let me provide a diagram of a detailed attack. The victim will first load all libraries in step 1, as we can see here, and then the appropriate weights will be loaded in step 2. So as the network starts doing inferences, it will trigger convolution operations, which will in turn trigger the GEMM driver in step 3. So these calls will be directed to the just-in-time GEMM library API in step 4. So first, a just-in-time GEMM library would check the code cache for the availability of the instruction sequences. So this would be step 5. But if that instruction sequence is not already available in the code cache, it will trigger the just-in-time compilation process, which will then in turn bring the instruction sequence to the code cache. So now we can see how an adversary would come into this picture. An adversary can load a simple model, and then as the adversary's model will perform these convolutions, these will be again driven through the GEMM driver. So these calls would again come to the just-in-time GEMM library API, which would again probe the code cache to see whether that instruction sequence is available. So in this scenario, if the attacker is using the same parameters as the victim, it will actually be serviced through the code cache. So this means that it doesn't trigger the just-in-time compiler. So now the attacker has a saving in terms of execution time. So now we can see how an attacker can come up with a score to rank different guesses and then figure out the correct choice. So in this slide, we can see the adversary's attack strategy. First, the attacker profiles and measures the execution time. So we refer to this as an isolated run. So in this compute environment, only the attacker is present. And then the attacker can figure out the expected execution times for different guesses. And then the attacker waits for the victim execution. And finally, the attacker runs her model with the guessed parameters and observe the execution times. So this is referred to as an observed run. So then we can easily come up with a score by looking at the isolated runtime and the observed runtime difference as a percentage of the isolated runtime. So if the parameters are being shared between the victim and the adversary, the observed runtime would actually be less compared to the isolated runtime. So this means that it would lead to a higher score. So the adversary can simply go through all the guesses and then record the runtimes, and if the guess which has the highest score would be the victim's secret parameter. So we can see a simple example of how this would work in reality. So here we're looking at a successful attack against the last fully connected layer. So let's assume that the final output size is known by the adversary. So this means that the attacker only needs to guess the number of input channels of the last fully connected layer. So the attacker comes up with guesses for the number of input channels. As you can see, the guesses are along the x-axis. And then in this graph, we can observe the time difference in microseconds on the left y-axis and the percentage time difference on the right y-axis. The highest percentage time difference allows an attacker to identify the victim's secret parameter. So in this case, it's recorded as 25. So the question arises whether this strategy can be applied to other cases as well. So in this graph, we're looking at different victim secret parameter and output shape combinations. And then for each scenario, we're looking at the success rate. So as you can see, in most of the cases, we have a good success rate, but when the matrix sizes increases, we see that the accuracy actually drops. So the reason is that when these matrix sizes become larger, the computations are no longer dominated by the just-in-time code generation time. So next we did the same attack on a convolution layer. So if we take a convolution layer, there are multiple parameters that we have to guess. For example, the kernel size, the stride, the pairing, and also we need to perform two simultaneous guesses. So hence we have a 3D graph. So on the x and y axis, we can see the input channel guesses and the number of filters guesses, which is also known as the output channels. So again, we can use the same score as before, and then this leads to the correct guess as 3 and 16 to be the same as the victim's secret parameters. So next, we did an attack on production DNNs on the last fully connected layer to identify the success rate in each of these scenarios. So as you can see, we record a good success rate for 10 of the popular DNNs which are being used. So all of these networks are trained on CFAR10 dataset. So next we perform an attack on a complete neural network. So in this case, we consider MobileNet V2. So first we show the top 1 success rate on the left hand side. So this means that according to the score that we proposed earlier, we are selecting the maximum score to be the victim's secret parameter. And then we show the top 3 success rate, which includes the top 3 candidates corresponding to the score that we presented earlier. So as you can see, when we increase from top 1 to top 3, the success rate also increases. So in the next slide, we'll see why this happens. So here we can see the previous graph. So let me just focus on the outliers here. So if you see the first layer with 96 and 24, the correct guess, which is bolded here, is actually the third option, where it's ranked as the second option 32% of the time, and then it's ranked as the third option 68% of the time. So the reason is that when you perform a neural network inference, multiple entries are available in the code cache. So although you're targeting one layer, it might activate another layer which is already in the code cache. So then this means that when an adversary performs this attack in a real environment, they would have to consider n number of choices. So this n would depend on the size of the neural network and other parameters. But the idea would be the attacker can figure out n number of options for each layer and then build a tree and then prune those options to narrow down the neural network architecture. So finally, this brings us to our conclusion. We presented a new timing attack on just-in-time optimized GEMM libraries and successfully extracted model hyperparameters. And our work is more to inform library developers and model users of the potential of such attacks. And we hope our work motivates new security research and make these libraries more robust so more people can actually benefit from these optimizations. Thank you. I would be happy to take any questions from the audience.